Hello everyone, welcome to my class. Now I'm going to explain about UV spectroscopy. Spectroscopy is nothing but it's a branch of science which deals with the study of interaction of electromagnetic radiation with matter is called as spectroscopy. Here matter is nothing but the compound which is going to be analyzed is called as matter. Electromagnetic radiation is nothing but which consists of various frequency ranges of band, and each frequency range band is called one particular name. For example, if you see from here left to right, this complete band is called as electromagnetic spectrum. Here, from here left to right, the frequency will decrease and energy also will decrease, but wavelength will increase. So here, because the left side waves are having the higher frequency, higher energy and shorter wavelengths, hence these gamma rays, X-rays are highly powerful, more energetic radiations. Then ultraviolet radiations, next visible radiations, next infrared radiation, next microwave radiations. The least energetic radiations are radio wave radiations. Here right side waves are longer wavelength, lower frequency and lower energy. So in this UV visible spectroscopy, we are using ultraviolet as well as visible radiations are using in the spectroscopy. So here energy of an electromagnetic radiation which follows this equation, that is E is equals to h nu. That means energy of radiation is directly proportional to the frequency of radiation. And also we can write this equation as like this also, energy of radiation is inversely proportional to the wavelength of radiation. That means if the frequency of any radiation is more, energy is more. If wavelength is more, then energy is less. Therefore, the energy of radiation which depends on frequency as well as wavelength of radiation. So, this is till now we have studied about the introduction of the spectroscopy. So, here UV spectroscopy is concerned with the study of absorption of UV radiation with matter. Here, this UV radiation ranges is 200 to 800 nanometers. Here 200 to 800 nanometers, 200 to 400 nanometers are called as ultraviolet radiation, 400 to 800 nanometers are called as visible radiation. Among ultraviolet and visible radiations are least energetic and ultraviolet radiations are more energetic radiation. Here nanometers are nothing but which are the units for the wavelength. If the wavelength number is more and energy is less or frequency is less. Here, whenever UV visible light, whenever it falls on the sample, then sample will absorb some amount of energy. Whenever sample is absorbed the energy, then in the sample, the changes are occurring in the electronic energy levels. Electronic energy levels changes will occur. Whenever changes are occurring in the electronic energy levels, along with each electronic energy levels, there also which consist of vibrational energy levels as well as rotational energy levels. That means each electronic energy levels which consist of vibrational as well as rotational energy levels. So whenever on the sample UV visible light whenever falls on the sample, whenever sample is absorbed by the light, then in the sample electronic levels changes will occur. So whenever electronic changes are occurring, also changes are occurring in vibrational rotational energy levels. Hence, this UV spectroscopy we are also called as electronic, vibrational and rotational spectroscopy. So here, whenever here sample is absorbing the light, then what will happen? Valency electrons absorbs those energy of the light. Then what will happen? Transitions are occurring from the ground state to excited state. Here, electrons are moves whenever the electrons are absorbed the UV visible light, then they move from the ground state level to the excitation state. This absorption is characteristic and depends on the nature of electrons which are present in the molecule. There are different types of electrons which are present in the molecule. In some type of molecules, only sigma electrons are present. So sigma electrons which are present in all saturated compounds. For example, if you take the ethane, in the ethane only sigma bonds electrons are present. So next another type of electrons are pi electrons, which are available in the unsaturated compounds. For example, if you take ethylene molecule, in ethylene molecule, sigma bonding electrons as well as pi bonding electrons are present. So N type of electrons which are present in all non-bonded compound electrons which are present in the compound. For example, if you take the acetaldehyde, in acetaldehyde, sigma bonding electrons, pi bonding electrons as well as non-bonding electrons which are present in the sample. So these are the different types of transitions, different types of electrons which are available in the molecule. So depends upon the which type of light, which energy of the radiation is absorbed by the sample, depends on the absorption of the energy, then different types of the transitions are occurring. So these are the electronic transitions. Whenever sample is absorbs UV visible light, then what will happen? Some changes are occurring. Which changes are occurring here? Electronic levels changes are occurring. Those electronic levels may be sigma to sigma star changes, or pi to pi star, or n to sigma star, or n to pi star. Because every bonding electron, there are also anti-bonding electrons also present. So here, first one is the sigma bonding. For sigma bonding, this is the anti-bonding of the sigma star. Next bond is pi bond. For pi bond orbital, there is also anti-pi bond also present, and this is the non-bonding electrons. And among all these transitions, here sigma to sigma star transitions, it requires a lot of energy, because sigma bonding electrons are high, very strongly held, hence which requires a lot of energy to transfer from ground state to excitation state. Whereas next pi to pi star transitions, because pi bonding electrons which are loosely held, hence which requires less energy as compared to sigma bonding electrons. Non-bonding electrons which are loosely held, that means no, which are loosely held and easily replace, easily moves from the ground state to the excitation state here. So here, so among all these transitions, higher energetic transitions are sigma to sigma star, next to n to sigma star, next to pi star, next least energetic transitions are n to pi star. So these are the different types of electronic transitions which are available in the molecule. So coming to the principle which is involved in Beer-Lambert's law. According to the Beer-Lambert's law, which states that concentration of a chemical solution is directly proportional to its absorption of light. So here, this is the our sample solution. Whenever we pass the light on the sample, then what will happen? Sample will absorb some of the incident light which is fall on the sample, then which takes some of the sample, then the remaining light is emitted by the sample. So always transmitted light intensity is lesser than the incident light. So as concentration of the sample is increases, more absorption of the light will takes place. So transmitted light intensity will decreases. This is called as Beer-Lambert's law. So according to the Beer-Lambert's law, the chemical equation is absorbance is equals to, which is directly proportional to the concentration of the sample solution as well as path length of this tube. So as concentration increases, what will happen? Absorbance also increases. So when we remove the absorbance and concentration which are directly proportionality, whenever we remove the proportionality constant, whenever we remove the proportionality, then we will get the proportionality constant, that is called as molar extinction coefficient. So according to Beer-Lambert's law, absorbance is equals to molar extinction coefficient, concentration and path length. And in this UV spectroscopy, we are using some terminologies. In that, first one is chromophore. Chromophore is chromophore is nothing but the group which exhibits absorption of electromagnetic radiation in the visible or ultraviolet region. That means the group is directly can absorb the light, either maybe the visible light or ultraviolet radiations. And here for chromophore, the examples are carbonyls, acids, esters, nitriles, ethylenes, or any groups which are examples for the chromophore. For example, if you take here, this is the ethylene molecule. In this ethylene molecule, here pi to pi star transitions are taking place. Here absorption, this compound absorption is taking place at 171 nanometers. That means this compound is directly absorbing the light in ultraviolet radiation. Hence, it is called as chromophore. Whereas if you take the acetylene molecule, this acetylene molecule also, because in this also sigma bonding electrons are present, pi bond electrons are present. But among sigma and pi bonds electrons are loosely held, hence easily undergoing to pi star transitions will take place. So here also this molecule absorbs the light at 180 nanometers. Whereas, for example, if you take the carbonyl molecule, in this carbonyl molecule, here non-bonding electrons are present on the oxygen. So, in this molecule, pi to pi star transitions will take place and n to pi star transitions are takes place. N to pi star transitions, because non-bonding electrons are very loosely held, so which absorption takes place at 290 nanometers, whereas pi to pi star transitions will take place by absorbing the light at 180 nanometers. So these are all examples for the chromophore, because these compounds are absorbing the light either ultraviolet region or visible region. These compounds are called as chromophore. Next terminology is oxochrome. Oxochrome is nothing but this compound is a saturated or unsaturated group which themselves do not absorb the radiation. But when present along with a chromophore, which enhances the absorbing properties of chromophore. Also, this oxochrome also called as color enhancing group. So, examples for the oxochromes are amine group, OH group, acid group, and alcohols group. These group generally directly it won't absorb the light in the ultraviolet radiation or visible radiation. But whenever which is attached to the chromophore, but which absorbs the light and also enhances the absorption wavelength and also enhances the coloring agent. For example, if you take here in this compound, benzene is a chromophore, because benzene which directly absorbs the light at 255 nanometer, hence it is called as a chromophore. But whereas if you take the phenol group, in this phenol, OH group is called as the oxochrome, because this OH group directly won't absorb the light in ultraviolet or visible radiation. But whenever if this OH group is attached to the chromophore, that is a benzene ring, then only benzene ring which absorbs the light at 255 nanometers. But here oxochrome which is attached to the chromophore, so because of the attachment to the chromophore, which increases the absorption wavelength, that is 270 nanometers. But directly it won't absorb the light. It won't absorb the light. It needs to attach with the chromophore. Whereas in this aniline structure, in this NH2 group also oxochrome, because it won't directly absorb the light. But whenever it is attached to the chromophore, it enhances the absorption wavelength. So here only benzene ring absorption wavelength is 255 nanometers. But here in this aniline, amine group is attached to the chromophore, so which enhances the absorption wavelength. So 255 to shift towards to the 280 nanometers. This is called as oxochrome. So another terminology which is used as bathochromic shift. This bathochromic shift also called as red shift. Nothing but when absorption maxima, that is wavelength lambda max of a compound shift towards to the longer wavelength, is called as bathochromic shift or red shift. So for example, if you take this effect is generally we will observe due to the presence of oxochrome. So here only benzene which absorbs the light at 255 nanometers, but whenever which is attached to the oxochrome, then which increases the absorption wavelength, that is 280. That means shift of wavelength towards to the maximum wavelength side, shift of band towards to the maximum wavelength side. So here it was earlier it was 255. Now because of attachment of oxochrome, it is moved towards to the 280. That means shift of wavelength towards to the higher wavelength side. That shift of band is called as bathochromic shift. Whereas hypsochromic shift are also called as blue shift. In this case, absorption maxima of a compound shift towards to the shorter wavelength is called as hypsochromic shift. Generally, this effect is due to the presence of a group causes a removal of conjugation or by change of solvent. Because of removal of conjugation, generally absorption wavelength will decrease. Then the decreasing absorption wavelength is called as hypsochromic shift. For example, if you see in this aniline, generally this absorption wavelength is 280 nanometers, because here, because nitrogen, all the nitrogen which containing the lone pair of electrons with this compound will involve in a resonance. Whenever which reacts with the acid, so nitrogen will get positive charge here, so no resonance involved here. So this absorption wavelength in this anilinium ion, absorption wavelength is 203 nanometers. That means shift of absorption wavelength towards to the lower side is called as hypsochromic shift. So earlier it was 280 nanometers, now it was 203 nanometers. So shift of absorption wavelength towards to the lower wavelength side is called as hypsochromic shift. So here this is the representation. This in this UV spectrum, generally on x-axis wavelength will be taken and y-axis absorbance will be taken. So with this figure, we will explain the what is red shift or bathochromic shift, what is blue shift or hypsochromic shift, and what is hyperchromic and hypochromic shift. Here, bathochromic shift is nothing but shift of absorption wavelength towards to the maximum side or higher side is called as red shift. Whereas hypsochromic or blue shift is nothing but shift of wavelength towards to the lower wavelength side is called as blue shift. Hyperchromic shift is nothing but increasing intensity. Increasing intensity is called as hypochromic shift. Hyperchromic shift. Whereas decreasing intensity is called as hypochromic shift. So these are the few terminologies which are used in the UV spectrometry. Here, absorption is increases due to increasing the conjugation, whereas here absorption is decreased due to removal of the conjugation. Here intensity increases as concentration increases, intensity will increases. As concentration decreases, intensity will decreases. So these are the few terminologies which are used in UV spectroscopy. And UV spectrometry, which spectrophotometer, which consists of several parts. Those are source of light, monochromator, sample cell, detector, amplifier, and recorder. Here, first part is source of light. Generally, in the UV spectrophotometer, tungsten filament lamp and deuterium lamps are generally used as a source. But here, tungsten filament lamp, which is generally used to produce the visible light, that range is 330 to 900 nanometers. Whereas deuterium lamp, which is used generally to produce the ultraviolet light, that range is 200 to 450 nanometers. So generally these two lamps, deuterium and tungsten lamps, are used as a source in UV spectrophotometer. And here, this is the schematic diagram of the single beam spectrophotometer. In this first, this is the light source, either maybe tungsten filament lamp or deuterium lamp will be taken here. From the light source, light will produce, and from here monochromator, only single wavelength light. Here the ranges of the light will produce here. From the monochromator, only single wavelength light will be produced. This single wavelength light will pass it on the sample solution. Now this sample will absorb that light and emit the remaining light. This absorbed light will be detected by the detector. Finally, recorder will give the output of the signal. Here, but in this single beam spectrophotometer, only one sample cell is present. So here, first we have to keep the sample in which we are going to dissolve, that solvent we have to keep, we have to run the spectrum. Under same conditions, again second time we have to remove that sample solvent solution. Again we have to keep here sample solution. Again we have to run the spectrum. That means to record the one spectrum, here to record the one sample, in single beam spectrophotometer, we have to run 2 times experiment. Whereas in double beam spectrophotometer, this is the light source, either deuterium lamp or tungsten filament lamps are used as a tungsten light source. From the light source, light will, all ranges of light will produce. From the monochromator, only single wavelength light will come out from this light, which is distributed into 2 equal halves. But because in this double beam spectrophotometer, 2 sample cells are present. So half light will pass through same time to the sample cuvette, another half light will pass through the reference cuvette. So here known in this double beam spectrophotometer, no need to run the experiment 2 times for each sample solution, because at a time we can keep here solvent and here we can keep sample solution. So at a time, this in this instrument, this light will distributed into 2 equal halves. Half light will pass on the reference solvent and another half light will pass on the sample solution. So finally, this difference of the light will be absorbed by the detector and finally recorder will give the output of the signal. So in the UV spectrophotometer, so total single beam spectrophotometer are available as well as double beam spectrophotometer is also available. So coming to the differences between these two spectrophotometers, in this single beam spectrophotometer, it measures total amount of light, whereas in double beam spectrophotometer, it measures percentage of light absorbed. And here it is not possible to compare blank and sample together. Here it is possible to compare blank and sample together. Here wavelength has to be adjusted every time. Here need not to adjust every time. Here it is a working is tedious and time consuming. But here working is fast and not tedious. So these are the differences between single beam as well as double beam spectrophotometers. And this is the representation of UV visible spectra. On the x-axis, generally it will take wavelength, which is units are nanometers. On y-axis, it will take the absorption. So here, as concentration of the sample is more, then intensity also more. Intensity also more. So which tells that the middle of this peak, which tells about the wavelength of that particular peak, that is represented as lambda max is 270 nanometers. So this is the representation of UV visible spectra. So coming to the applications of UV visible spectroscopy, which is mainly used for the characterizing aromatic compounds and conjugated olefins. That means if any given compound, unknown compound, whether that compound is having any aromatic compounds or any unsaturated compounds like ethylene, butadiene, any such type of the compounds are present or not, we can determine with the help of UV visible spectroscopy. Another importance is it can be used to find out molar concentration of the solute under study. And also another important of application is it is one of the best method for determination of impurities in organic molecules. So these are the few applications which are present in the UV visible spectroscopy. So thank you for your patience listening.